In this video, I'm going to talk about some of the formulas that are used in mechanics of materials that use the area moment of inertia. These aren't properly part of statics, but as we're learning how to calculate area moments of inertia by integration for composite areas and things like that, again, I want you to appreciate why you need them. And once you get the mechanics materials, you're going to use these formulas a lot. And so I want you to appreciate that as we're wrapping up statics this semester. So area moments of inertia, which is the symbol is capital I, and it's defined by the integral, for example, of Ix is the integral over the area of y squared dA. Arises frequently in mechanics materials. And so you'll see moments of inertia tabulated, for example, in beam tables. You actually scroll down in this handout. There's shear and bending moment diagrams for common loading situations. This is a point load in the center of a beam. This is a uniform distributed load in the center of a beam. These beam tables are for angle shapes. And these beam tables here are for like wide flange shapes, W shapes. And if you look in the table here, this top line is a wide flange beam or W shape. It's 8 inches deep and it's 67 pounds per foot. And there's dimensions of the beam, the cross-sectional area, how deep the beam is, the web dimensions. So the middle section is called the web. The flange dimensions, the width and the thickness of the flange. Over here, you have I, which is the area moment of inertia, about the XX axis, which is basically this axis. And there's a area moment of inertia about the Y axis. So if you turn this beam on its end, on its side, and loaded it like a beam that way, you would be concerned with the area moment of inertia about that axis. If it's oriented in its normal orientation with a flange at the top and the bottom, then you're interested in the area moment of inertia about the XX axis, and that's here in the table. So you'll use those numbers a lot in mechanics materials. So what are some of the formulas where you see I arise? I put an example here on this handout, and this handout is in the OneDrive and it's on the website. And so I'm not going to go through this example of a plain board or a wooden board, but I just want to show you the formulas down here. So in a bending stress and deflection problem, so if you have a beam and you load it, for example, with a point load, there are stresses that develop in that beam. And so the bottom of the beam is in tension and the top of the beam is in compression. If those fibers are going to fail, it's typically going to be the tension fibers in the bottom of the beam. The middle of the beam is called a neutral axis. And these are called bending stresses. It's interesting that at the middle of the beam or at the centroid of the beam, those bending stresses are 0. So one of the reasons you learn to find centroids in the centroids chapter is when you get to mechanics of materials on beam stress and beam deflection problems, you're going to be doing centroid problems all the time. And you're going to find the neutral axis or the centroid, and then that'll be the neutral axis. And then basically the bending stress is very linearly outward from that centroid. The formula for bending stress is this, well, the symbol is sigma. So sigma is that bending stress that acts on that face. And so sigma is equal to MY over I. And so M is the bending moment at that point of the beam. Y is the distance from the neutral axis or from the centroid out. And of course, Y is the maximum at the outer fiber of the beam, either the top of the beam or the bottom of the beam. Those are the outer fibers of the beam. And the denominator is the area moment of inertia about that particular shape of beam. The larger this moment of inertia is in the bottom, the lower the bending stress is. for the same bending moment and the same y, or the same distance from the centroidal axis. And so a larger moment of inertia, for example, a W-shaped beam on its end will have a larger I, and it will resist bending more. So if you actually go down to this table that we looked at for this W shape, the I about his XX axis is 272 inches to the fourth. The I about his YY axis is 88.6. And so it's a third. It's a third about the y-axis. So that's why you stand an I-beam on its end. It's 3 times more resistant to bending and bending stress at that orientation. Another interesting formula is the deflection in the middle of the beam. And so if you look at these beam tables, if you look at the shear and bending moment formulas, the maximum deflection is given here, and it's given here. And it's hard to read the formula, but the formula for the point load is the maximum deflection for a point load in the middle of the beam. The maximum deflections in the middle, and it's equal to the load times the length cubed divided by 48 EI. And so E is the elastic modulus. It's the stiffness of the material. So the stiffer the material, for example, is steel, the deflection is going to be less. For a less stiff material, for example, a wood, the deflection will be more, for the same loading, the same length of a beam. But notice in the denominator, you have this I, which is the area moment of inertia. And so a larger I, for example, an I-beam on its side, will have, for everything else being equal, the same load, the same length of the beam, same material, a larger I will mean less deflection in the middle. That's one reason why I showed you the yardstick example, just to show you that the same yardstick at one orientation resists bending because it has a large I in that direction, but then the yardstick on its side is a much smaller I, and so it's very susceptible to bending. And remember, we mentioned that the area is further from the axis of the central axis, neutral axis, and that results in a larger I. So remember, when you're calculating I, remember I is a function of the y squared dA. And so the farther you can move a material away from the neutral axis, I increases by a square of that distance for the same area. And so there's significant benefit in moving that area farther from the neutral axis, for example, by putting those larger flanges on a beam. Now, of course, a beam has to have a central web that's large enough, because the web carries the shear stress in a beam. That's another story. But so you need a web that's large enough to carry the shear stress, and large enough to keep the beam together. But for bending stress purposes, by putting those flanges, top and bottom flanges further out, creates a larger I. And so that's giving you, again, some background in mechanics of materials as to why we care about area moments of inertia and now in statics as we're learning these. One more interesting thing we're going to do in this unit or in this chapter in statics is we're going to talk about, so the area moment of inertia for a given area varies depending on the axis that you choose. And so at some axis across that area, it's going to have a larger moment of inertia, and another axis it's going to be smaller. For example, this W beam, we saw that the I was large about the x-axis and small about the y. If you look at this other picture, this is like an L-shaped or an angle shape. And like this first line is a 6 by 6, so where this is 6 inches by 6 inches. And in one direction, I is 35.5. In the other direction, it's 35.5, and because this is 6 and 6. However, there's a ZZ axis that actually is a minimum I that's smaller than the IY and the IX, because the Z axis is oriented at such an angle that it passes closer to the centroid of this material. So all of that material is closer to the z-axis. So the I of the shape about the z-axis is a minimum. It's smaller than the x and the y. So ZZ is the minimal axis. Now, one of the things we're going to do in this chapter is, so give it an IX and give it an IY for a given area. We're going to talk about finding I around another set of axes that are rotated some theta from that original coordinate system. And again, there's some orientation where I will be a minimum and some orientation where I will be a maximum. And that's called area of moment of inertia transformation. And we're going to use equations for that, and we're going to use the Moore circle for that. This is an introduction to how you use area moments of inertia in mechanics materials and why we're studying them now in statics.